Section 2A is going to be about dimensional analysis. Basically, what it is a technique that we can use to convert from one type of unit to another type of unit. The way that it looks is going to be a chain of fractions that are being multiplied together. Here's an example of a problem that we'll be doing in a little while here, number 15. Don't really worry too much about what the units you see here, but what I want you to visualize is you have a fraction being multiplied by a fraction, being multiplied by a fraction, being multiplied by a fraction, and eventually you're going to get a number that's going to have different units than what you began with. Okay, now that one's a little bit of a longer one, but I think it highlights the technique that we're going to be used can be applied to something that might be a little bit more complex. All right, so for the beginning part here, the introduction, and really all we're going to do is address a few things about the concepts of units. Like we have units to powers, and then we also have the word per that we need to understand what that means. All right, so the first couple questions, what type of units would you use to describe a distance from Austin to San Antonio? You could have written, we probably wrote miles, but you could write something like kilometers, or can't think of another one off the top of my head that would be reasonable for that type of a distance you can measure. But there's all kinds of things that are out there for distance, like inches, feet, meters, and stuff like that. This would probably be miles or kilometers. So the next question, when you're buying a house and you want to know how large it is, that's going to be advertised as square feet. Okay, and the real thing that's happening here between A and B, questions A and B here, is that we have units that are what we call one-dimensional. Then we have units that are two-dimensional. So that word squared refers to that exponent of a little 2. So we have square feet. Literally speaking, what that represents is how many square tiles of a foot, like square foot tiles. You usually see them in a classroom or a hospital, the little square tiles. It's asking how many of those does it take to cover the surface. So different than just measuring a distance. One of the other, actually, let me kind of build off of that one, go all the way down here. When we abbreviate something like that, it could show up like this as yards squared. Okay, and so there's these abbreviations how we write things, and like if we said yards squared or square yards, then you would just use a little exponent over 2. You can also do things that are cubed. So if we're talking about an idea of volume, we could do cubic units, and you might have something like cubic feet, so you get feet to the 3rd power. So one of the things we're addressing in the beginning is just that units can have powers on them. That's going to come back at the very end, I believe, with some other types of converting, but we're going to kind of talk about it real briefly here. The other big thing is using the word per. Like you've heard a lot of these before, like miles per hour, dollars per hour, this type of thing. So the word per, you want to interpret that as the word, or as the mathematical operation division, which of course is going to help when we get to the dimensional analysis. And I showed you setting things up as fractions, because fractions are division. Okay, so one of the key things to using dimensional analysis is that when you multiply by these fractions, you want the fractions to represent a value of 1. This might not make total sense until we start doing problems. I'll try and go back and keep explaining this part here. But you want to create these fractions that are representative of a value of 1, so that when you multiply by that fraction, it doesn't actually change what it's worth. It's just if we're really sneaky about using, what do they call them here? These unit conversion fractions that we can change the units that are on it without actually changing the size of the value. Okay, so we're going to start off here with some things that we should know. 12 inches is the same thing as 1 foot. Okay, so that's a unit conversion, that 1 foot. By the way, the word unit really refers to one of something. Okay, so 1 foot is going to be worth 12 inches. Okay, and that's a true fact. We should all know that. The way that this is going to get applied when we do our dimensional analysis is going to be in the form of a fraction. So you could write the fraction as 12 inches over 1 foot, or 1 foot over 12 inches. Now here's the neat thing about it is if you look at the fractions, because 12 inches is the same thing as 1 foot, each of these fractions is actually worth the value of 1. Okay, and that's going to be important when we start trying to multiply and not wanting to change the value of something. All right, we get to practice on our own here. They ask us about seconds and minutes. The unit conversion is that 1 minute is going to be equal to 60 seconds. Okay, so then when we try to apply this one a little later on, we'll do 60 seconds over 1 minute, or we could do 1 minute over 60 seconds. So these are choices that you get to have when you're doing the problems, like which way to set the fraction. The truth in that, though, like deciding between which one you're going to use is going to be super easy because you look for something that precedes it and then it tells you which one to use, and it's not that hard of a deal. All right, so let's try this out. What we want to do here is take, and I like the way that they started here because we're already starting with a rate type thing where we have a per in there, because you'll see these later where we don't actually have the per. This is actually a really good way to start out. All right, we're going to convert 20 feet per minute to feet per second. Okay, so if we look at the units, this one actually has two parts to it. It has the feet, and then it also has the minutes part to it. The units that we're going to finish with here are still going to have the feet, but we're changing the seconds. Okay, so where it begins is taking whatever we start with, like that, and you need to make a fraction out of it. So per is the division. We're going to put the 20 feet over 1 minute. Okay, and that's where we begin. So this is what we have. And then what we're going to do using dimensional analysis is multiply by a chain of fractions until we get what you want. In this case, there's only one more link to this product that we're going to do. Okay, so what we want is to keep the feet, but change the minutes to seconds. So we're going to take the unit conversion that relates minutes, I should point here, that relate minutes to seconds, which is what we've got right above, this area here, and we're going to multiply that by that fraction. But what we want to do is make sure that when we set up that fraction, that the units we want to remove, which are on the bottom in this case, we want those units on the top. So we're going to make sure we put 1 minute over 60 seconds. So one of the ways you can definitely justify why I want to do this, or try and explain it to ourselves here, is that when we end up multiplying these two fractions together, the rule of the multiplying is going straight across and then reducing. Or you can reduce before you multiply straight across. I don't know if that was shown to you with general fractions, but it's a good technique. So the minutes are going to be on the top and the bottom. They're going to cancel out. So if you wanted to get rid of units that are on the bottom, make sure that they show up on the top so that you can just cancel them. Okay, and when those are removed, there's nothing else that matches as far as units because this is a one-step problem. Those are out and you're going to end up with feet over seconds. So now multiplying across, we get 20 feet because 20 multiplied by 1 is 20 feet. And you have 1 multiplied 60, 20 feet per 60 seconds. Okay, for the most part, the unit conversion part is done with that, but we do want to clean up the problem to make it look a little bit nicer. Go ahead and divide your number. So we got 20 divided by 60. The zeros will cancel. We get 2/3. 2/6. That's going to reduce down to 1/3. So as a decimal, it'll appear as a 0.3 repeating. That's what that little bar is, 0.3 repeating feet per second. Or if you want to, because I know that one looks a little bit odd, you could do this as a fraction. You could do 1/3 feet per second. Okay, so that's an option. It's how you can write it as well, and both are fine. There's not one that's actually better. It's just more likely what you prefer to look at. All right, let me come back to one more thing here so we kind of understand a bit more about like why this works. This is something that we start with and we convert it into, say, that one, right? And along the way of doing that, we multiplied by something else. Right? There's multiplication and there's a fraction here. Okay, but the neat thing is that this fraction is worth 1 whole because a minute is the same thing as 60 seconds. This is just a fraction where the numerator and the denominator are the same thing. So if we multiply our starting value by something that's equivalent to 1, we're getting back something that is still the same. Anytime you multiply by 1, you get back the same thing. But the way that we do it, we're really sneaky and we're able to change the units that show up in there. All right, at the top of page 2, you have a couple of tables that are going to give you some unit conversions that we can look at. Let's see, you got 6 multiplied by 3, so 18. You have 18 total conversions that are here. As a side note, You are not responsible for memorizing any of these. That would be a lot to ask of you, and it would not be not an easy thing because of all the decimals that you're going to see in here. So don't worry about that part. You can have this to reference. It's a matter of being able to apply them. All right, so number 7, you plan to go to France and you know that the speedometer is going to be in kilometers per hour. Okay, not our miles per hour, but kilometers per hour. You would like to know what 60 miles per hour is in kilometers per hour. Okay, and it's a good question because we all have a sense of what 60 miles per hour feels like, and if that's a typical speed that you might be driving, then you might want to know what number would match up as far as the kilometers per hour. Not that understanding why we're converting stuff is like for purpose here. We just need to know how to do it. All right, what is the speed that you're asking to convert? We want to change 60 miles per hour. What are the units that you want to convert to? We want to get to kilometers per hour. All right, so we're not really concerned with changing our time part here, right? The hours is all the same. What we're looking at trying to do is change miles to kilometers. So what we're going to do is go to our table and we're going to look for a spot where we can find a comparison between miles and kilometers. This, of course, is going to be the 1, but it is located over here. Okay, so it tells us that 1 mile is going to be equal to 1.6093 kilometers. Okay, that's what we want to use. Now, it did say in the instructions that we want to write it in 3 forms, but I figured that wouldn't quite be necessary for this video. These are the 2 things that are the same as each other. When we do get to the point of our dimensional analysis, you're going to stack them as a fraction, one way or the other, and that just depends on what we're trying to cancel out. And it's one of the really great things about dimensional analysis, because as you're building the problems, it sort of just tells you how to set things up. Okay, so let's take a look at this. Here's where we begin. There's the fraction that's going to be 60 miles per hour. I went ahead and changed miles to mi. You'll see me do that a couple times in here, just so that it doesn't get confused with maybe meters or something. So I kind of go back and forth with that. Okay, but here's where we begin. We got the 60 miles per is your division bar, and then you've got the 1 hour. That would be on the bottom. By the way, it doesn't read as 60 miles per 1 hour, but we're supposed to interpret it as 60 miles per hour, so that's 1 hour, so you want to put a 1 that's down here. Okay, what we want to change are the miles. We want to keep the hours, we want to change the miles. So we want to make sure that miles end up on the bottom of the next fraction. Okay, and then the unit that we're going to change miles into is going to be on the top part. So we're just going to take these 2 things that we know they're equal to each other, and we'll make sure that the 1 mile is on the bottom, the kilometers is on the top. Okay, so it's not always going to be that way. It just depends on what we actually start with. There are reasons why they might be flipped in different directions. Okay, so the miles are going to end up canceling out, sort of like you're reducing a fraction, which is going to leave you with kilometers over hours. So that's exactly what we want. So now what we do is we multiply across and then we divide if necessary. In this case, you're not going to need to divide because your denominator is just going to be a 1. Right? You're going to get 1 hour, 1 times 1. The top, you're going to need to multiply the 60 by that number. So let me get out my calculator for that. So 60 times 1.6093 is going to give you 96.558. And those will be kilometers. All right, now as far as how many decimals you should keep, in this course it's going to be a little bit debatable in which way, how far do we really want to go with things. This isn't too bad because it goes out to 3. In the context of the problem, that might not be really so necessary. You'd probably just round this to like 97, something like that. For me, maybe, this is just a maybe because I'll change my mind time to time. I'll probably round just to 1 decimal and call it 96.6. And then write the units like that. The only reason that I like to do at least 1 decimal when I round versus going to a whole value, which would make more sense in the context of the problem here, is because when you leave 1 decimal, it at least gives the idea that the number wasn't like a perfect conversion. I would go with it. So that's kind of me, but very flexible in how we do the rounding, as long as we're doing the rounding technique correct. So you should know how to do that. All right, so questions 8 and 9. These I always think are pretty good questions to highlight the reason that we want to use something called dimensional analysis, because it brings in a set of units that we've all seen before, we've used them, but generally I don't think that our American public like really has an idea how much like size these things are, right? So we buy things as gallons or half gallons. You buy things in liters, like a 2 liter bottle of soda, right? We purchase our milk in terms of gallons and we purchase soda in terms of liters. But we probably don't think too much about how they really compare to each other, because you never have to buy milk in liters and you never have to buy soda in gallons, right? Okay, let's see what we need to do here. A toddler in 1 year is going to drink 12 gallons of milk. So how many liters would this be? Maybe you're traveling overseas again here. Okay, so how many liters, basically the question is, how many liters is 12 gallons of milk? Okay, so here's where we begin. We start with 12 gallons. Now, it wasn't 12 gallons per something. That's not how this one was designed, right? It was just simply 12 gallons. But for the way that we're going to do things with dimensional analysis, you want them to be fractions. So if it's just a simple number with a unit on it, like 12 gallons, go ahead and write 12 gallons over 1 or whatever you have. Just place it over 1. In the end, you're going to end up with an over 1 situation anyway, and it'll get removed. But it's important that we set it up as a fraction, because what we want to do is multiply by our conversion fractions as we go along. All right, so what we need to do, you can already see the numbers here, but what we would need to do here is go to the table and see if we can find a connection between liters and gallons. Okay, so that one ends up on the little table as well here. 1 gallon is going to be equal to 3.785 liters. So again, you don't need to memorize that stuff. It'll just be here, and you need to know that you can find them. Okay, so these are the two we want, and it's either going to be gallons on top of liters or liters on top of gallons. But the way that we set these up, we're always going to put the 12 gallons over 1, or whatever our thing is over 1. So that tells us that the next fraction has to have gallons in the bottom, which means that liters have to be in the top. You then assign the numbers that went with them, which is 1 and 3.785. So it's a neat way to think about it, right? Because we have gallons on the top, you have to have gallons on the bottom to cancel. And if gallons are on the bottom, then liters are going to be on the top. So everything just kind of finds its place once you have your numbers. All right, now we reevaluate our situation to see what we need to look at. The bottom is just going to be a 1, right? We don't even have any units when we multiply this. Okay, on the top, it's going to be liters because gallons are out, but we're going to multiply 12 by 3.785, and we're going to get 45.42. That one's got the approximate symbol. What was it? 45.42. It has the approximate symbol. So I'm guessing they want us to round this off to the nearest liter, which will be approximately, we'll just say 45 liters. Man, it's close to like 45 and a half, but because they got that symbol, I'm just gonna go ahead and round there. I don't know. And technically it does round down, so that would be our answer if we want to approximate. All right, number 9, also getting into stuff that we might not be super used to here. Quarts are 1/4 of a gallon. So if it's already a little bit weird thinking gallons to liters, okay, liters to quarts is going to be just as more complicated, because now we got to think like 1/4 of a gallon. Now you don't actually have to do that in the conversions here, because like the 4th part, you don't have to do that because it's already got 1 quart is equal to that amount there. Now if you multiply that by 4, you're going to get that number with a little bit of rounding issues there. Anyhow, 1 quart is equal to 0.9464 liters. Don't ever round the numbers that they give you there, just at least use all that. All right, 16 liters, 2 quarts. That means in your first fraction, you're going to do the 16 liters over 1. There's no per, so just over 1. Okay, that then tells us the next fraction has to have liters on the bottom, and then what you want to change it into on the top, which is going to be quarts. So liters and quarts. Once you have that, go ahead and place the numbers that you see in the table next to those units, and everything's going to work itself out. Liters are going to cancel, you're going to get 16 times 1, which is 16. On the bottom, you're going to get 1 times our decimal, so you get your decimal back here. That will be the number of quarts that we get. You should not state your answer like that because it doesn't really mean anything to us. Okay, so we'll divide them. We'll take 16 divided by 0.9464, which is going to give us about 16.9. We'll go with that. Okay. One thing, because I'm thinking about it right now and I'll share with you, is what's really cool about the dimensional analysis. And I've liked this ever since I learned it. I think it was in 9th grade math is when I first saw it. But I really like the idea because you never really had to compare the sizes of stuff and figure out what to do with the numbers. So even if you had the numbers, it's kind of hard to figure out, what do I do with them? Do I multiply? Do I divide? What operations am I using? And if your technique is dimensional analysis, it just tells you what to do. All you have to do is start with a fraction, make sure that you have units matching top and bottom so that they'll cancel, and the rest takes care of itself. It's a pretty cool thing. We never thought, this question you never even think about, all right, why do I divide 16 by that number? I mean, you could now, because now you know that this is worth 1 quart. So if you divide it by the number, you can get the number of quarts that you need. But you didn't have to think about it, which I think is really cool. All right, questions 10 and 11. These two questions, what you're converting in here are things that I don't think really anybody in the general public would have trouble converting. But the purpose of the questions is to show you that we can do a longer chain of multiplying. So all the problems before this were only using 1 fraction. These are going to show you using 2 fractions to get eventually where you want. Okay, so the first, what we want to do is convert 180 inches into yards. Okay, now even in this question, I think they kind of drew it out a little bit. A yard, yes, is 3 feet, but a yard is also 36 inches. I don't know how common knowledge that is for everybody else, but in like my garage where I'm recording this right now, I have yardsticks, so I know a yardstick is 36 inches on there. So if I wanted to convert 180 inches into yards, what I would do is just divide 180 by 36, which you're going to see at the end of the problem. So that's sort of helpful that you do get to see that. Okay, but here's it all broken down and stuff, supposing that you didn't know it was 36 inches. We can start with 180 inches. And let's say we don't know how to go straight from inches to yards, but we do know how to go from inches to feet, right? I know that 1 foot is equal to 12 inches. So I can start with just this part here, and it's going to convert my 180 inches into feet, right? Just make sure my inches are on the bottom. Those are going to cancel out, and let's kind of think about the math, what it would look like here. You'd have 180 times 1, which is 180, and you're going to divide that by 1 times 12, which is 12. So 180 divided by 12, and you would have converted it into feet. But we don't actually want to stop there. And you could do that at its own problem and then reset if you want, but it's easier just to now build off it. Say, okay, I don't really want feet. What I want are yards. So I'm going to put feet on the bottom and put yards on the top because I know that 1 yard is equal to 3 feet. So now the feet cancel, and you're just left with yards. And you can do this as long as you need. Keep changing one unit to the next. So if you don't have a direct path from what you want to what you need, you can go through as many steps as are needed here. Ultimately, let's check it out. You get 180. You get the 12 times 3, which is that 36. It's at the bottom, and as I'd mentioned it before. So it all works out. $180 divided by 12 is going to be 15. So we're going to get 15 yards for that one. All right, 11. This, I think, is a question that if you've never heard of dimensional analysis, you'd be all right with it. Like, we shouldn't. If you have any concept of time, you shouldn't have any trouble with it. All right, converting 5 years to hours. Okay, let's not look at it as dimensional analysis for the moment. Let's cover that up. Okay, converting 5 years to hours. It's almost like you can think backwards on this. You can say, well, there's 24 hours in one day. There's 365 days in a year, and I've got 5 years. So if you were just to multiply 24 times 365 times 5, you're done. You've got it. Okay, but the purpose of the activity is to let you practice dimensional analysis for all types of problems, because you're going to look at this and you say, I can do that one on my own, and that's fine. And by the way, I don't really care if that's how you do the problem. Whatever works and you know it's working, great. But what we want to show you here is that you can do a string of multiplication and it also works. Well, string of multiplying fractions, I should say. Okay, so we actually begin with 5 years. We're going to convert 5 years into days first. We're going to put years on the bottom, 365 days on the top. Years are going to cancel, and you've got 5 times 365, which is your number of days in 5 years. But we didn't want years, we wanted hours. So we're going to convert 1 day into 24 hours. Days cancel out, and look what we still get. We get the product that I was trying to describe there at the beginning. And now I type it in. We get 43,800. Oh, questions 12, 13, 14, and 15. All of these questions in some part are going to be referring to the table that is up here. This is a bit confusing. I'll be honest with it, but I'm going to give you a pretty solid hint here on what you should do with this table to make all these problems go a little bit better. Okay, so let's talk about what the table is first. It's about converting currency, which fluctuates all the time, just by the way, but January 2017, this is what like some of them were. Okay, so what we're doing is we're comparing all of these types of currencies to the US dollar. But you've got these two columns here, right? Okay, the first column, actually, if you read the title here, it's the dollars per foreign. That's per foreign currency. So let's just take the first one right there. Okay, per foreign currency. So all of these are actually dollars. It would have been helpful if they put that in there. It's in the title, so you don't have to, but it'd be helpful. All of these represent an amount of dollars that's going to be worth one of these things here. So 1 British pound is worth $1.22. 1 Japanese yen is worth $0.0086. So it's hardly anything. That's what we were going to contemplate. The peso, one peso is worth about 4.5 cents, is what that is. Okay, now the other column is going to be foreign per dollar. Okay, so these are not dollars here. This is that we get 0.8191. I don't know if I said that right. Anyway, you get that amount of British pounds per $1. Okay, so this is $1. I guess you write that backwards, didn't you? Oh, us Americans. $1. Okay. Euros, you get 0.9449 euros for $1. You get 21.86 pesos for $1. Okay, so what we really have here is two columns that essentially compare what we want, like both. They both do it, right? It's just a matter of perspective that these are all dollar amounts compared to one of these things. These are all going to be how much of those currencies to $1. So what I'm going to say from the very beginning here, take that guy out. Don't even look at that one. So that way you have a consistent way of how you're using the table. Okay, these are always these units compared to $1. All right, number 12 is really just going to break down that comparison. Since I really talked a lot about that, I'll just show you the answers. British pounds, we got $1, and then there's the conversion factor, and I already described that one, so I'm not going to get too much into that. Okay, 13. Suppose traveling from the United States to Europe, use the table to convert European euro, $2. Okay, so they want you to take from both of the tables. So again, I don't really want to talk about both of these, but you've got, okay, so this one right here is referring to that. So we got that amount of euros compared to $1. Okay, but you could do the same thing using this number, which will be the amount of dollars per €1. So if you're trying to use both of the columns, it might get confusing. So if I just scratch that one, then I don't ever even pay attention to this one either. And that'll be my suggestion with this. Let's just be consistently using the second. You could use the first, but I like the second one because $1 seems very consistent to me. Okay, now we actually do some conversion now. All right, how many euros is $200 worth? So we begin with $200. It's not a purse, it's just 200 over 1. Okay, these are dollars. The next fraction is going to need to have dollars in the bottom and euros in the top. Okay, and because I'm using this column here, then I know that 100% of the time I'm going to have $1. Then I got these other things. Okay, so if I need dollars on the bottom, then I know that I'm going to put $1 on the bottom. And if I'm converting to euros, I'll just go look up euros and put that number on the top. And that's what you'll see here. Okay, so now the dollars are going to cancel. The ones aren't going to do anything. And if I just multiply those two numbers, I get 18.898. A lot of these come with 4 decimals, so I'll just keep the whole thing. 898. What do we got here? Euros. All right. This is going to be a per problem. Cantaloupe sell for $1, or not $1, sell for 1.8 euros per kilogram in Belgium. What is the price in units and US dollars per pound? So just kind of get a comparison of what we know. Oh, and they went ahead and helped us out with the conversion for kilograms to pounds. That is, I'm pretty sure it's on the other table somewhere. Yep, it was over there. It was on this. So all these will be provided for you. They just try to save you some time here. Okay, so here's how we start, right? If we look real close, you get the purse. So this is the top, and then this is going to be the bottom. Okay, so you got a 1.8 euros to 1 kilogram. And we want to change both of those units. This is a really good problem for dimensional analysis. We got to change the euros to dollars, and we also got to change the kilograms to pounds. There's not a rule in which one you need to change first, but choose one, completely change it, and then build off of it to change the next one. So I think I probably started with the euros. Converting the euros, that means I need to have euros on the bottom, and then I'm going to have dollars on the top. And since I'm using that second column here, I definitely know that I got $1 on top, and it's going to be 0.9449 euros on the bottom. So let's see if that's how I actually did this one. Yep, there it was. Okay, so euros are going to cancel out. And we got dollars, which is exactly 1. All right, now cool thing about dimensional analysis is we can continue to build off of this. Just stop looking at the dollars right now and start looking at the kilograms. Next, I want the kilograms to go away. So my next fraction is going to have kilograms on the top, and it's going to have pounds on the bottom, because I need the kilograms to cancel with the other kilograms. So we're going to have the 1 kilogram on top of 2.205 pounds. All right, so kilograms cancel out. We got our pounds on the bottom. All right, now checking our units for the very end part here. Across the top, your unit is dollars. We usually have the dollar symbol in front, and that's so confusing on this. But anyway, we're going to have dollars per, and our unit on the bottom is pounds. Okay, so our units are coming out correctly here. What I was trying to do is write down the units first, but because of where we place our dollar symbol, it kind of messed that idea up. All right, across the top, I'm multiplying 1.8 times a bunch of ones. All right, can't do anything with that, so I'll just kind of clear that out for a moment. For the bottom, I'm going to multiply these two numbers, which, by the way, I noticed, hopefully you did too there. But I'm not going to re-record it for that one. Okay, I had an extra 0 in there. 49 times 2.205. Okay, yeah, so that's going to be our bottom there. I had to really think about the calculation guide. This is almost 1, so we're getting back pretty close to that number. Okay, so that will be the denominator. We're going to take 1.8, we're going to divide it, and if you have a calculator that can recall answers, you can just recall that other number and divide by it so it's as accurate as possible. Or just take enough decimals and you'll be fine. Looks like we're going to get that, which is going to be, since this is dollars, we're going to put 0.86 per pound. You could do a little slash if you want. That'd be fine. Per pound. All right, so about 86 cents per pound is what that converts out to. All right, 15. Let's see. So I know what I'm doing here. I'm going to be changing my money, and I'm going to be changing my sizes here. Oh, this is that half-gallon problem that we got. Okay, 0.8 liter bottle of Mexican wine cost 100 pesos. At that price, how much would half a gallon jug of the same wine cost in dollars? It's kind of a weird thing. Okay, look, what we're really going to do is try and figure out the cost in dollars per gallon. Okay, a half gallon means just cut the whole thing in half, divide by 2 at the end of it. Now you're going to see how I end up working into the dimensional analysis here, but sometimes these little weird things like a half gallon, just convert into a gallon and cut the whole thing in half. Divide your answer by 2 and you're fine. All right, so we begin with, they didn't tell you it as a per, but if you're doing anything like money and weight, money and volume thing, then you should do the money over this because it reads a little bit better, like 100 pesos per 0.8 liter. It's normally like per liter, but that's fine. Anyway, if you do have money compared to like a volume or a size amount sort of thing, then try and do the money on the top. I can't say 100% money is going to be on top, but in this case, it does work. Okay, so 100 pesos compared to those liters. It's not a unit rate because it's not 1 liter, but it's something that we know, which is a different problem here. All right, so we're going to convert pesos into dollars. That means I'm going to have pesos on the bottom. And because I'm only using the second column from the table that's up top, I know that I'm going to have $1 on top, and I'm going to have 21.86 pesos on the bottom. And there's that. Okay, so that's going to take care of our currency unit. We'll get us $2. And now we ignore all that and we just think about how do I go from liters to gallons? Okay, I think we looked that one up a little earlier. That's a 3785. Yeah. Okay, so since liters are on the bottom, you want liters on top, then you're converting into gallons, so put gallons on the bottom. Those are the numbers taken from the table. Okay, and for the most part, you could do the problem this way, find out the dollars per gallon and then just divide it by 2 to get your half-gallon jug. But, technically you can convert as well a gallon to a half a gallon. 1 gallon is going to be equal to 2 half gallons. There, 1 gallon is equal to 2 half gallons. So gallons will cancel out. And look, all you're doing is dividing by 2. Same thing that we already would have known. So it's really neat to see how the dimensional analysis still applies in some unusual cases. All right, let's see. Across the top here, multiplying 100 by that number is super easy. You're going to get 378.5. That would be dollars, right? That's our units on top. All right, on the bottom, this will take a little bit more math. I got 0.8 multiplied by 21.86 multiplied by that 2 I have at the end, and I get 34.976. Okay, so now I'll divide those two numbers. And we get that. All right, so I paused the video there for just a second because I looked at that answer and I was like, what in the world is going on here? Well, when you leave out a decimal point, it changes numbers significantly, right? All right, so let's put that decimal in there. I was like, what? 1 cent for half a gallon of wine is probably not going to be correct. All right, much more reasonable answer here, which would be about $10 and let's say 82 cents. $10, 82 cents per half gallon. All right, for 2A, part 2, these last couple of pages that we have to look at here, this is going to go back to something that was mentioned at the very beginning of the activity, which was the squared units and the cube units, so units to powers sort of thing. All right, for these, I sort of use dimensional, this is me personally speaking, I sort of use dimensional analysis to an extent. I don't quite go as far as how they're going to describe it here, but I have found that students do pretty well with it from this perspective. So I'll try and share both ideas that I have here. Okay, one of the most important things that we get at the beginning is what's taken from this picture here. Okay, suppose we're talking about a unit of area, and you've probably heard things like square feet. I mean, we talked about it for the house, but you can also measure things in square yards, because if it's a very large thing, you might not want to use a little unit like a square foot and go with something larger like a square yard. Okay, here's where it gets tricky. And if you acknowledge this part at the very beginning, it's going to help out stuff a lot. Yeah, 1 yard is equal to 3 feet. That's true. But 1 square yard is not equal to 3 square feet. You can't just throw that word squared in there and it works. Okay, and here's a picture that describes it. All right, the big box all the way around here is going to be 1 yard by 1 yard. So you get 1 square yard. See, it's literally a square. That's why we use the word squared. And later with cubes, they're cubes. They actually look like little blocks. Okay, so you got 1 big square yard. Each of those sides is worth 3 feet. So if I break it off here, I got 1 foot, 2 foot, 3 feet. And I can do the same thing here. Now, if you extend out those lines and break it apart, you realize that it takes, count them all up, it takes 9 little squares, square feet, to make 1 square yard. Okay, it's not, when it's in a straight line measurement, it's 1 to 3. We know that. But when we start talking about area, it's actually going to be a larger number. Here's what it really is. If the conversion factor is 1 to 3 in what we call one dimension or straight line measurements, in area, it's going to be 1 squared to 3 squared. Now, of course, 1 squared is 1, and 3 squared is 9. So that's how we get to the 1 to 9. That's where that's happening in there. And you can apply that technique to like any other case that you might get for measuring like area and converting like square area. By the way, there's only a couple examples that we really ever use, which is going to be this one, and then also like square inches to square feet. Sometimes we branch out and we do some other unusual ones, but those tend to be the big ones. All right, now over here, we're going to talk about dimensional analysis and how that can be applied in here. It's a bit tricky, but try and go with it. For me, this is what I always just use, because that fact never changes. 1 square yard is 9 square feet. So if you want to just convert, just use 1 to 9 and it'll get you there. All right, but here's how we can break it up. All right, so what we know, 1 yard is equal to 3 feet. If we want to convert 1 yard squared into square feet, the thing is you can look at that unit as yards squared as being yards times yards. That's what squaring things are. It's multiplying by itself. So these are the same, right? You got 1 yard times yard, and that's the yard squared. Okay, so let's go down and start setting things up. This is what we begin with. You can do this, we'll call it expansion. Break apart that power, so you see yard, yard. And what that tells us then is we need to remove the yards in our dimensional analysis twice. Okay, so we're going to set up this fraction first, which is 3 feet to 1 yard. That is going to allow you to cancel out these yards, so only one of them. And that yard now changes to feet. Okay, so if we multiply by that same fraction one more time, the yards are going to cancel out, and you get another feet. So you would just replace both of those with feet, which means we got 3 times 3 is 9. You get 9 feet, all right? And 9 feet is the same thing as 9 feet squared. So it's a neat way how dimensional analysis still applies, and you can separate. I don't always use it because I know that it's a 1 to 9, and then I can just apply that all the time, but and it never changes, so you can do that as well if you want. But this is a little neat thing you can do. All right, so let's see what we got. All right, so in my case here, if I want to convert 5 square yards to square feet, like on my own, so we'll do it this way in a moment here. But if I want to do it, all I'll say is, all right, if I've got 5 square yards, I'll just multiply it by 9, which will give me 45. Because every one of the square yards has 9 square feet, so 9 times 5 is 45. Yeah, so it's going back to kind of the way we may have done converting before dimensional analysis. But here's how it works out. We're just going to replace the 5. So it's the same thing as what's above there. You're replacing the 5 in for the 1, and then you're going to do the 3 to 1, the 3 to 1. So yards cancel, and yards cancel, and you get 5 times 3 times 3 feet, which is ultimately still going to get you to 45 feet squared. All right, number 2, inches and feet, as I alluded to a little earlier. If we want to figure out the number of square inches, that's what we want to conversion. We want to get this conversion factor. We want to know the number of square inches in a square foot. All right, 1 square foot is going to be equal to blank square inches. Okay, well, let's kind of think about what we did with this box here, and then I'll do the dimensional analysis. The bigger unit would be the feet, so your big box would have been 1 foot by 1 foot. But then if you were to break 1 foot into inches, you would get a total of 12. And then you get 12 going down there, and if you extend all the lines going across in the directions, you would end up with 12 times 12 boxes, which is actually 144. And I always think that one's a little bit crazy that in 1 square foot, you have 144 square inches, but if you were to really imagine dividing up the box, you could see it. It would make sense that they'd all be in there. You'd have 12 in each row and 12 rows of 12. Okay, so here's how it's done using the dimensional analysis. Your feet squared is going to be broken up into feet. So we're going to want to convert inches and feet to cancel out that first foot. Inches and feet to cancel out the next feet, which gets you inches, also called inches squared. And our numbers that would apply here would be 12 inches to 1 foot, 12 inches to 1 foot, so you get 12 times 12, which is 144. Again, that's a fact. Just like 1 to 9 for yards and square feet, you've got 1 to 144 for these units, so you could actually just apply those if you want. Now here's one that's just a really unusual kind of case. I don't see this one with practical applications, not at least in my world, but it's good practice one here. The other thing I think is kind of confusing here is they got mm, which actually stands for millimeters. It does not stand for meters times meters. Okay, so if you got millimeters squared, you've actually got mm times mm. So there's a whole lot of m's going on in this problem. Okay, but what we want to do is convert 2,000 millimeters squared to square meters. All right, now a square meter is approximately the size of a square yard. I always forget which one's bigger or smaller, but I think the meter's a little bit larger. Okay, so it's a big square. A millimeter squared is about that size. It's super tiny. Okay, so yeah, we got 2,000 of these guys, but how much is it gonna make it something really huge? It's gonna be a very, very small number when it's said and done. All right, so let's see what we got though. All broken up. 2,000 millimeters. We want to convert millimeters to meters, and here's the conversion factors here, that 1,000 millimeters makes a meter. Okay, so I want to get rid of millimeters, so I'm going to put mm on the bottom with a meters on the top. It'll be 1 to 1,000 that way, so these will cancel. We'll do that one more time to make sure that we get rid of the next set of millimeters and leave us with m times m, known as meters squared. All right, taking a look at the math, we've got 2,000 divided by 1,000 times 1,000, which is total of 6 zeros there, so 1,000,000. By the way, these 3 zeros are just going to cancel with those two, or those 3 at the bottom, sorry. But I'll just go ahead and type it in as complete numbers. Divided by 1,000,000. And you're going to get 0.002. Okay, and that would be read as 2 thousandths of a square meter. So if you were to take a square meter and break it up into 1,000 equally sized pieces, it's only going to be worth 2 of them. So it's super tiny units, trying to convert into something large, yeah, you're going to get a very small amount of that thing. All right, for our last page here, what we do is got some practice problems for the area and volume stuff going on. So a little bit more than what we did on the page before this, which was just coming up with the conversion comparisons, but now like an application of them. All right, for the first question, number 4 here, they give you 2 different strategies on how to do the problem. My preference is going to be doing the first one, and I'll try and explain it when I'm done with the problem there. All right, what we've got is a rug that's 3 feet by 6 feet, and we want to convert it into square yards. Okay. What I prefer and what it's going to ask you to do here is to calculate the area in square feet first, then convert it into square yards. Okay, so if we just multiply the 3 by 6, we get 18 feet squared. All right, now remember, we've got that sort of solid conversion factor that you can use if you want, which is the 1 to 9 comparison. So if I've got 18 feet squared, I can put feet squared on the bottom, yards squared on the top, and not worry about splitting this into like feet, yards, business, right? I can just cancel the cancel the feet squared with the feet squared, and I get yards squared, and I'm done in one step. Okay, just make sure you use the right numbers that are 1 to 9 and not a 1 to 3, because 1 to 3 would be if you did them individually. All right, so then ultimately this is just 18 divided by 9, which is going to be 2 yards squared. The other strategy that's next to it that I don't really like is to convert each of these into yards, and then you can just multiply them. So 3 feet is 1 yard, and 6 feet is actually 2 yards because it's 3 feet per yard. Then you can just multiply those, and you also get 2 yards squared when the yards multiply there. And though that might sound very convenient, the reason that I don't like this is in a problem like the one that we're looking at, these convert into yards really nicely. But there are a lot more problems out there that the dimensions that we're going to use aren't going to convert nicely. Like if I gave you 4 feet, well, how many yards is 4 feet? I'd have to take 4 and divide it by 3 feet, like 4 feet divided by 3 feet, and it tells me I get 1 and a repeating 3 yards. And that decimal right there is just going to cause a lot of trouble when you're trying to do things, because you don't want to round it off. And you'll notice that if you do it in this version here, just calculate your area and then convert, you're not going to have to worry so much about decimals showing up. All right, question number 5 is not much different than what we did in number 4. It does suggest maybe you draw a picture of a rectangle, but I didn't draw it for this one because I felt like just length times width is fine. Okay, it is going to be the backwards version of the problem though, because you're going to start with yards and then we're going to convert that into feet. So anyway, I would just multiply these 2 numbers together to get the square yardage, which turns out to be 240. Then take the 240 yards squared over 1. I like using this factor that 1 square yard is equal to 9 feet. So as long as I put the yards squared on the bottom, they're going to cancel out, and we're looking at just multiplying 9 times 240. It should give you 2,160. And those are feet squared. Okay, so I don't do complete dimensional analysis with it by splitting up my units as yards, feet, but I still use it. In this sense, I just choose to use a new factor that we came up with. All right, 6, this one, yeah, it gets us into volume here, length times width times height. We don't do any complex shapes in this course, so area is really just going to be length times width, and the volume is going to be length times width times height. They're all like rectangular in their way. All right, pool that has all the links are going to be in yards, and we want to, oh, there it is. We're going to convert it into cubic feet in a little bit. Okay, so we're going to figure out what the volume is in cubic yards. So even in this problem, they're really trying to get us to do strategy number 1, which is the one that I like anyway. All right, so you multiply all your dimensions together, got it, and it turns out to be 60 cubic yards. All right, so what volume of water could it hold in cubic feet? Now, what we haven't done is come up with a direct conversion factor that's going to relate cubic units. So for this one, I did break it up, right? If I've got yards 3 times, that means I need yards 3 times on the bottom. And we're doing yards in feet, so then we're going to have 3 feet across the top 3 times as well. So all of these yards are going to cancel with each one of those. You'll get left with feet cubed, which is what we want. Everything on the bottom is a 1, so no big deal. 3 times 3 is 27. 27 times 60, I don't know. 27 times 60 is going to give you 1,620. Okay, now though, let me go ahead and throw out something here. If you are converting cubic units, there's also going to be a consistent factor, right? So in cubic units, if it was 1 to 3, that'd be 1 yard to 3 feet. In volume terms, they're going to be cubed, which means you got 1 cubed to 3 cubed, so you get 1 to 27. 3 to the 3rd power 27. So if you wanted to, you could have just done this problem with 1 cubic yard is 27 cubic feet. But if you don't want to do that, because I haven't done too many examples with that, that's fine. You can continue to break that apart. All right, 7, we got a hot tub pump that circulates that amount of cubic inches of water per minute. How many cubic feet of water does it circulate per minute? So minute, time's not changing, that's good. Okay, so we got that number, cubic inches, over 1 minute. To get rid of the inches 3 times, you need inches 1, 2, 3 times on the bottom. We want to go to feet, so it's going to be 12 inches to feet. That'll get us to our feet cubed per minute. And we just multiply or divide and all the things we need to do. Okay, so now we know that the 12s are all on the bottom. So we're going to take 6,912 divided by 12, divided by 12, divided by 12, or you can divide by the product of all those 12s. But you end up with 4 cubic feet per minute. Okay. All right, and last, number 8, just kind of closure on what do we expect from units. Linear is length, square is area, cubic is volume. How would you see those written? For a second, I was going to try and write down like different types of units, and I thought, no, really the idea here is it's about powers. If something's just a length, it can just be like feet. But if it's going to be area, like feet squared, then it's feet squared. Volume is going to be feet cubed. Okay, so I thought about showing different types of units and numbers there. But really what this is about is just understanding that if you're talking about area, there's going to be a squared, and if you're talking about volume, there's going to be a cubed that goes along with it.